We finished 1.1 and here we are, 1.2. If you guys look at the top of your page, what does it say 1.2 is about? Displaying what kind of data? Quantitative. So 1.1 was all about categorical. We were talking about categories, bar charts, pie graphs. We're shifting gears. Categorical. We're going to talk about how to display quantitative. Thank you. Good. Golly. We are shifting from categorical to quantitative. There we go. Data. So what are quantitative data? Data that is measuring or counting something, numbers, right? So quantitative data. One of the most common graphs that we use with quantitative data is a dot plot. You guys know how to use dot plots, right? Yay! So let's look at some dot plots. Brian and Jessica have decided to move and are considering some different cities. The graphs below show the daily high temperature in June, July, and August for each of these cities. Help them pick a city by answering the questions below. First of all, what type of graph are these? We've already said that. What are they? Dot plots. Yay. All right. Each graph has about 90 dots. Can somebody tell me what does each dot represent? It is 1 day's daily high temperature. Very good. It is 1 day's daily high temperature. Perfect. So even the lowest dot on each of these graphs, it's not a low temperature. It is a daily high temperature of that amount. It just happens to be the lowest daily high for that city in those 3 months. All right. We are going to look at the first three, the top three graphs. We're going to look at them first. First of all, please look at those three graphs and tell me, what do you notice? They look to be the same graph, don't they? This data was fully made up. This is all just made up crap right here, okay? Usually data that I give you guys is real, but this is made up. All right, so we have three dot plots here that are exactly the same, but what is different?
The range.
So their range is the same, but because okay, so let's talk about what is range. What is range? Think about middle school. What does range mean? How do you find the range? It is the highest number minus the lowest number. And wouldn't all three of these have the exact same high minus low value? Right? So while yes, the high and the low number are different, they have the same difference. Okay, so all three of these actually have the same range, but I know exactly what you meant, Kyle. What I believe Kyle's saying is basically where they're located on the scale of temperature, right? So it's like the values of the highs and the lows. When we look at a graph, most of the time our eyes focus on the center of it. And so what we would basically look at here is like the location of these are different, but specifically speaking, we're going to look at the centers. The centers are shifted. Which of these cities would have the highest temperature? Yeah, good. A is the hottest. And which city would be the coldest? Yeah, B would be the coldest, or the coolest, I guess. Good. Awesome. All right, now we're going to look at graph C versus graph D. Graph C versus graph D. I would tell you guys this, the centers are actually the same for those two graphs. They're centered around the same value of about 80, but what is different? The range is different, absolutely. Specifically, the city D is more spread out, right? So the spread, right, how spread out or how varied it is, and the range for sure. But we're going to specifically speak about the spread. The spread is different here. D has a wider spread. D has a wider spread. Cool. Now we're going to look at D versus E. D versus E. Both of these have the same center. They actually have the same spread, meaning the same range, right? They have the same high, and low, high. What's different, though?
There's more on specific temperature.
Good. E is more concentrated in the middle, right? But it has these two little guys out here. One on the low side, one on the high side. What do you guys think those little dudes are called? Absolutely, those are called outliers. So outliers are present in E. Outliers are present in E. And then our final group here, we're going to look at C versus F and G. So that's C versus the bottom two here. The centers are actually the same. Okay, here's why. If I think about trying to balance these graphs, like on my finger or on some sort of like a fulcrum or a triangle or whatever, if I were to try to balance it, it would balance about here. These, while they're not exactly symmetric, they would balance because of the way that it is shaped. They would balance about the same. So they all balance about at 80. All of these have the exact same range. If I take the high minus the low, they would have the same range or the same spread. None of them have an outlier. So the only difference is the way that they're shaped. Or the way that they're shaped. So their shapes are different. Shapes are different. Specifically, graph C is what we would call approximately symmetric. If I look at just kind of the overall shape of that, it's fairly symmetric. Okay, I'm not talking about little details, but for the most part, it's pretty symmetric. F and G are what we call skewed. F and G are skewed. We'll talk about what direction they're skewed in here in just a second. So these are the 4 characteristics that we're going to talk about anytime we are describing a distribution of quantitative data. We're going to want to talk about these 4 things: the center of it, the spread of it, the outliers, and the shape. Which of these cities would you guys want to recommend to them? Which one do you think is the best city with temperatures? You like B? You like things a little cooler? I like that. Especially with it being 8 million degrees outside right now. Very good. Awesome. So, 4 things. Let's talk about those 4 things a little more. When you are describing a distribution of quantitative values, you're going to talk about those 4 things. Shape. You're going to say, is it approximately symmetric? Maybe it's skewed. Maybe you're even going to see that there's a gap or something, and you want to talk about the gap that might be there, okay? You're going to talk about those things. That's how you're going to describe the shape. Outliers. Outliers are pretty important. For now, we're just going to say that an outlier is any data value that is like visually away from the rest of the data. Like you can see a space between them. That's going to be for now. Later, when you're older and wiser, I'll tell you how to do it mathematically. But for now, we're just going to look at it and go, yeah, that kind of looks like an outlier, and that's going to be totally fine for now. So this is just an unusually large or small value. It's going to be very obvious on the graph. It's going to look different. It's going to be off to itself. Center. So there are 2 ways we're going to talk about the center of a quantitative data. One of them is the mean. The other one is the median. All right. Have you guys ever done mean and median before? Oh my gosh, so much, right? How do you find the mean? Add up all the numbers, divide by the number of numbers. Yay! What's another word for mean? Average. Very good. Median. How do you find the median? You basically list all the numbers in order, and then you like, there it is, right there in the middle. It's the middle number when the data is in order. Easy, right? So we kind of like to use these at a specific time based on what kind of shape you have. Your mean is when you have approximately symmetric data. We really like to use the mean. Anytime we can use the mean, we would prefer to. And with symmetric data, the mean is a very good representation of the data. And so anytime you have symmetric data, we're probably going to use the mean. You can use the median, but what is true, let's see if you can think about this for a second. What would be true about the mean and the median when you have symmetric data? They're going to be very close to the same, right? Your mean and your median are going to be pretty much the same when you have symmetric data. Okay. The median, however, is different when you have skewed data. So anytime you have any kind of skewed data, you're going to want to use the median. The reason for that is because the mean is affected by the skew. And so we don't really want to use that as a measure of the center of the data because it can be thrown off pretty quickly by some weird data. So that's kind of how we're going to go with that. And then our spread. Anytime we are trying to describe a distribution, we want to talk about the spread. There's lots of ways to talk about how spread out the data is, one of which is range. The problem with range is that it is a single number that tells you the difference between the low and the high, and it doesn't really tell us where on the number line is that data. So for spread, we actually kind of prefer to list the low and the high. So we're going to actually list the low to the high value. We can very quickly then get the range by subtracting those two. There's going to be some other things we're going to do with spread to talk about how spread out data is. But for now, until you get a little older, we're going to just go with low to high. So 90% of the stuff that we're going to do in this class is quantitative data. And anytime you have a graph and you're asked to describe the distribution of the quantitative data, you're going to have to remember to talk about the shape, the outliers, the center, and the spread. How in the world are you supposed to remember that? Socks! Socks! Shape, outliers, center, spread. Socks! You're going to bring your socks to AP Statistics. SOCS stands for shape, outlier, center, spread. Shape, outlier, center, spread. What does SOCS stand for? Shape, outlier, center, spread. Let's go. Very good. Shape, outlier, center, spread. Do you guys know Miss Child? Okay, Miss Child's a math teacher. She's all the way down the hallway here, okay? She loves socks. She does. And so we want to tell her right now that we're talking about socks because I want you guys to make sure she can hear you when I ask this question. What does SOCS stand for? Shape, outlier, center, spread. Take that, Miss Child. Very good. SOCS, shape, outlier, center, spread. Got it? I can also promise you this. If you ask any former student of an AP Statistics, whether me or Coach Ramos, if you ask them what does SOCS stand for, they can tell you shape, outlier, center, spread. This is probably the most commonly used thing in stats. SOCS, shape, outlier, center, spread. What does SOCS stand for? Shape, outlier, center, spread. Yes, very good, very good. You got it. All right, we're going to talk about the detail of shape for a second. Shape. Okay, I'm excited. Shape, symmetric. Here is a symmetric graph. Here is also a symmetric graph. Here is also a symmetric graph. Yay, symmetric graphs. Symmetric graphs just mean that there is symmetry. They are about the same on each side, and that's a symmetric graph. Unimodal. Unimodal. What does una mean? One, okay. Modal. 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 What does that make you think about? Mode. The mode. Do you guys remember what the mode is in a data set? It's the number that appears the most, right? Mean, median, and mode. Mode is the number that appears the most. If you are making like a dot plot of some data and you're stacking a value up many times over because it's repeating, it's going to create a peak. And so mode or modal is also another word for peak. So what does unimodal mean? One peak. You got it. So here is a one peak unimodal, well, I just said the same thing twice. Here is a one peak symmetric distribution. Here is a one peak non-symmetric or skewed distribution. Here is another one peak, just skewed to a different side. So unimodal works, but it doesn't distinguish between symmetric and skewed, which is the biggest thing we want to do, is distinguish between symmetric and skewed. Bimodal, what's bimodal? Two peaks. So this is going to be our camels, our deformed camels, our other way deformed camels. Okay, so yes. So we can have bimodal and skewed as well. We can have bimodal and symmetric. Okay, skewed left and right. Skewed right and left. Here we go. Skewed to the left. Why does that? Oh, that's why. Skewed to the left. Sorry. It's fine. It's okay. Skewed to the left. Looks like that. Skewed to the right. Looks like that. Everybody always thinks I have them backwards, but I promise you I do not. When I say something is skewed, what does that make you think? It's messed up, right? Most of this data is chilling right here together, but there's some messed up data off to the left, okay? The data is messed up to the left. On this one, most of our data is chilling right here, but our messed up or skewed data is off to the right. Now, what does SOC stand for?
Shape, outlier, center, spread.
Let's go. Okay, cool. And where do you put your socks?
On your feet.
On your feet. I love feet, you guys. I do love feet. You know why I love feet so much? Because it helps me remember skewed left and right. Watch this. Doesn't this kind of look like a big foot right here? Look at these little toenails. Man, these are delicious. Look at these. Oh my gosh. Look at skewed to the right. Oh yeah, look at this guy. Skewed to the right. Oh man. Oh my gosh, look at these. These are amazing. Oh my gosh, we broke our pinky toe. Look at that. Ouch. Okay. So look. Skewed left looks like your left foot. Skewed right looks like your right foot. So like if you're trying to remember which way is this skewed, just look at your feet. Just be like, hey feet. Oh, that's right. Got it? Also, I do not have a foot fetish. I just don't know that. I just need you to know that. It's just from the core of my soul. I don't. I swear. But here's the other thing. It makes an impact, and you won't forget it. So there you go. Uniform. What does it mean for something to be uniform? The same. It's all the same. Here would be a uniform data set. It would look like that, right? Boring. It's uniform because every value is the same. It has the same amount. It has the same amount in every data set. So I'm going to be honest with you guys. We do not deal a lot with uniform data. It's just not in the real world. The real world is not uniform, as you know. We are very different. Some of us have foot fetishes. Some of us don't. It's very different, okay? Do you guys have any questions about shapes? Feet! No. What does SOC stand for?
Shape, outlier, center, spread.
Spread. There we go. Shape, outlier, center, spread. I love it. All right. So let's check out these graphs on the board. These are not on your paper, so don't think I forgot anything. These are just, I'm just threw these up here. All right, let's look at the top left. What do you guys think about the shape of this top left graph? I would say this is fairly symmetric, okay? This is pretty symmetric, okay? When you're talking about shape, you're kind of talking about the overall shape. You're not looking at the little details, okay? We're looking at the overall shape. So this is fairly symmetric, okay? Good. What else? Unimodal, for sure. Yeah. Very good. All right, let's look at B, top right. What do you guys think about top right here? Skewed which way? Very good. We got big old toe right here. Look at that guy. Man, that toe is giant. Yes. You got to draw the toenails. I'm just saying. All right, so there it is. That is definitely skewed to the left. What about this one right here? This is bimodal. Very good. If this was skewed, which way would you say it's skewed? This would be approximately left skewed if it was skewed. I'm not saying it is, but this toe had some this foot had some terrible damage to it, and then it's got it's like I don't know what happened. Either the middle toes got cut off, or I don't know, something's not right. All right, over here. What do you guys think about this? Yeah. This is definitely skewed to the right? We got teeny tiny toes here. Yeah. Okay, cool. Any questions about shapes? Think about your feet. Think about those scrumptious feet. Yes. All right. Love it. I love it. All right, dot plots. Here's a dot plot, you guys. It shows the scores on a 20-point quiz for each of the 30 students in a statistics class. What was the highest score on this quiz? 20. How many people scored a 20?
What?
10. Very good. What is the lowest score? 13. How many people got a 13? 2. And what was the least frequent score? 14. Very good. Do you guys have any questions on how to read a dot plot? Perfect. Then let's do an example. Nitrates are organic compounds that are the main ingredient in fertilizers. When those fertilizers run off into streams, the nitrates can have a toxic effect on fish. An ecologist studying nitrate pollution in 2 streams measures nitrate concentrations at 42 places on Stony Brook and 42 places on Millbrook. The parallel dot plots display the data. I want you guys to know that parallel dot plots is really not that fancy. All that means, when you see that it's a parallel whatever, that just means it's going to share the x-axis. So notice that each of these graphs is stacked on top of this one x-axis. I don't have 2 different x-axes. It's easy to compare from top to bottom or whatever. So that is a parallel dot plot. There is a dot on Stony Brook at 12. What does that particular dot mean? What does it represent? One of the nitrate measurements was 12 milligrams per liter. Very good. One of the measurements was 12 milligrams per liter. Yay! That's absolutely correct. I guess if I was being specific, I would say at Stony Brook, but it says it in the problem. All right, next question. Says, what percent of the nitrate concentration measurements for each stream exceed 10 milligrams per liter? So let's talk about Stony Brook. How many of the measurements were greater than 10? 2. 2 out of 42. I mean, I don't know. Do you guys know what that is as a percent?
4.76.
Look at that. 4.76. You guys all did that in your head, right?
Yep.
Yeah, you did. I love it. Perfect. Look at Millbrook. Look at Millbrook next. How many of the data values exceed 10 for Millbrook? 11 or 10? 11? 11 going once? Going twice? Sold. 11 out of 42. Any guesses on what that is as a percent? 26.19%. Let's go. Nice. Okay? Perfect. Describe the shapes of the two dot plots. I'm going to be honest with you guys. These are maybe not the easiest to figure out just because of how few data values there are, and they're pretty spread out. So these could go either way, really. For the most part, if it's kind of on the edge, you would get credit if you went either way. So, but with that being said, what do you guys think about Stony Brook? What shape do you think Stony Brook is? Yeah, I can definitely see a right skew on that one. Very good. So this would be skewed right. Yep. You could say skewed right, right skewed, slightly right skewed, a little bit right skewed, skewed right. Okay, cool. Millbrook. This one's even harder. What do you think about Millbrook? I think this one really could be either left skew or symmetric. I really feel like you could go either way and be right. So either way would be fine with me. Maybe you could even say a slight left skew. That would be fine too. Either way. All right, I think we have beat this dead horse about dot plots. Do you guys have any questions about dot plots, how to read them, how to interpret them, how to do things with them? Perfection. Let's switch to stem plots. Stem plots. Oh my gosh. I know for a fact that you guys have seen stem plots before, but it's been a hot minute. So I want to make sure you remember how to read them. They may have been called stem and leaf plots back in your day when you did them. Okay, so stem and leaf plot or stem plot. So this is a stem plot. This is about the U.S. Drug and Food Administration limits the amount of caffeine in a 12-ounce can of carbonated beverages to 72 milligrams. That translates to a maximum of 48 milligrams of caffeine per 8-ounce serving. Data on the caffeine content of popular sodas in milligrams per 8-ounce serving are displayed in the stem plot. So, let's see if you can read this. What is the lowest amount of caffeine in one of these cans that was measured? In this data, what is the lowest amount of caffeine that was measured? Okay. 15 is correct. 15. What is the next observation in order? 15. What would be the next number? 16. What's the next number? 20. What's the next number? And then? Okay, do you guys see how to read it now? What's the highest amount of caffeine in a can? 47. How many of the cans had 35 milligrams of caffeine? 3 of them. Right here. Okay. Do we see it? Ish? Okay. Perfect. If I were to label these for you guys, so these are called the stems. Those basically just tell you what the tens place is or whatever of the number. And then your leaves are going to be the ones digit, basically. Now, that is how it is for this data set because these are whole numbers. It could also, I just want you to know that it could also be 1.5, 1.5, 2.0, 2.3. If these were decimals, I would have to indicate that in my key, which we're going to talk about a key here in a second. But these particular numbers, because the problem told me we were measuring milligrams per caffeine, that's the only reason I knew that this was 15, 15, 20, 20, all that stuff. All right. I want you to also look at the stems and notice that we have 1, and then we have 2, 2, 3, 3, 4, 4. The fact that we have 2 2s, 2 3s, 2 4s, that's called splitting stems, okay? Why do you think they split the stems like that? Well, actually, let me ask this first. How did they split the stems? Almost, not 1 through 5. 0 to 4, and then 5 to 9. So this row right here would have the numbers from 20 to 24. This would have 25 to 29. This would be 30 to 34, 35 to 39. So they split them. They cut the group in half. Okay, why do you think they did that? That's literally the answer. It is just easier to read. It's easier to read, and you can see better the details of the data. It's better than it just being one long line for the 2s and one pretty long line for the 3s. Goodness. All right, so it's easier to read. Easier to read details of the data. Perfect. All right, let's talk about that key that I was just saying. Put a big giant star here for a key because this is the number one thing that people forget when they make a stem plot. They just lose their mind and forget to make a key. There was no key here, so we're going to remember to make a key. To make a key is very easy. You just pick a number. Usually it's a number that's in the data set, right? So you pick any number in the data set. I'm just going to go with 25. You put like a 2 and then like a slash and then a 5. Or a 2 and then like a vertical line. And you just say that equals 25 milligrams caffeine, right? You're just defining what that number means. The reason that this is important is what I was talking about a minute ago. Here's like an example. If these had been decimals, 2/5 might equal 2.5, right? That's why a key is important. So we know which way to read the stem or the stem plot. Does that make sense? Awesome sauce. Describe the distribution. Oh my gosh, you guys, we get to use our socks. Socks. What does socks stand for? There it is. Shape, outlier, center, and spread. Shape, outlier, center, and spread. How in the world are you supposed to see the shape? Wow. Now, with that being said, always make sure you're looking at it from lowest to highest, left to right. Right? So what shape do you see in this distribution? Yep. I would definitely say that this is probably a slight right skew. So my shape is a slight right skew. You want to see the toes? Oh, yeah, baby. Look at these toes. Oh, yikes. Okay, cool. Yeah. Woo. Yikes. Oh, my gosh. What's going on with that middle toe? I don't know, man. This might be bimodal. I'm just saying. It could be bimodal. Actually, I think it is. Let's just stab somebody with that thing. All right, outliers. Outliers. Do you guys see any data that is like visually away from the rest of the data? No, not really. So there's none. Center, center. All right, look, I told you that center can be either mean or median. I mean, do you guys want to add all these numbers up and divide by the number of numbers? No, bro, that's going to take us forever. We ain't got time for that crap. So let's just go find it, right? Now, you have to be a little careful with a stem plot. You got to make sure that when you're marking numbers off, you're going in like this to get to the middle, okay? So also, your stems are just there to read the numbers. They're not a part of the data per se. So we're only going to focus on the leaves. So I don't know, maybe go every like 3. That makes it easy. So like 1, 2, 3 of the high numbers, 1, 2, 3 of the low numbers. Or I said that backwards, but whatever. 3 of the low numbers, 3 of the high numbers. Do another 3 of the low numbers, 1, 2, 3 of the high numbers. Again, notice I'm going inwards like this, okay? Going in like that. 3 more. 3 more. 3 more, 3 more, 3 more, 3 more. Oh, yeah, okay. Where's the middle? 28, good. When I am talking about center, I have to make sure that I say what center I'm using. Am I using the mean or the median? So I'm going to put median equals 28 milligrams. Nice. Spread. Again, I want to make sure that I notate the low to the high. So what did you guys say the lowest number was again? 15 milligrams. What's the highest number? 47 milligrams. Boom! Spread. Socks. Done. What does socks stand for?
Shape, outliers, center, spread.
Let's go! All right, you guys understand stem plots now? Yeah. Perfect. Let's make it harder then. Yeah! Let's talk about back-to-back stem plots. He said, why is this a thing? All right, so look, we got some back-to-back stem plots here. We even split those stems up. This shows, okay, we need to have a serious conversation, y'all. This shows the data that was scored by the Dallas Cowboys. Future Super Bowl winners. This is their year. This is their year. We're winning the Super Bowl by 80. I just need to make sure we're clear on that, okay? Dak the King Prescott is taking us to the ship. Mark it down today, you guys. I just let you know how the season... In fact, they should just give him the trophy right now. They should give the trophy to the Dallas Cowboys, led by Dak Prescott. We got this. All right, back to the problem here. So this is the number of points scored by the Dallas Cowboys and then their opponents during the 2014-2017 season. There were 48, 2014 to 27, whatever. There's 48 games on this thing, left and right. What was the Cowboys' highest scoring game in the sample? 42. So, on this particular example, our stems are in the middle, right? But we still use those stems in the same way. So, 42, good golly. 42 is the highest number. Now, ignoring the outliers on those opponents, what is the shape of the opponent's distribution? Again, feel free to take your paper and turn it to the side if you would like. What is the shape of that opponent's distribution? Oh, yeah, look at those feet. Yes. I love it. It's skewed to the right. Okay, skewed to the right. All good? Perfect. The center. What is the center of the opponent's distribution? I'll give you a second to get there. On this one, you do know that there's 48 values, so you could just count to the 24th value. That would work too. I know. Every once in a while I'm right. That's crazy. The center of the opponent's distribution. All right, does anybody have an idea of what it might be? 19, very good. Okay, real quick, before you guys finish up, let's just pretend the Cowboys' distribution looked like this. Let's just pretend it looked like this. Okay? Please tell me, if the Cowboys' distribution had looked like that, what shape would that be?
No.
It would be skewed left. Why is that? Lowest to highest. So you have to be slightly careful when it's backwards. All right, we'll finish this page up tomorrow.